Well, good afternoon, everybody. So I'll be talking to you about our project titled Major Advances in Understanding of Collisionless Plasmas Enabled through Petascale Kinetic Simulations. And of course, this is a very ambitious title, so I'll try to narrow it down to some specific issues. The setting for our work is that we're trying to understand the connections between the Sun and the near-Earth space environment. So this field of research is sometimes referred to as space weather because there are certain similarities that you can draw between the dynamics of this complicated system and the atmospheric weather. And so this cartoon shows some of the major processes that are in play. We have the Sun, which dominates the dynamics in the solar system. The Sun outputs plasma both in terms of the relatively steady stream of particles known as the solar wind, and also in much more intermittent, sometimes violent events such as coronal mass ejections. Whatever the form, this plasma may come towards the Earth and interact with the internal magnetic field of the Earth, shaping it and forming the magnetosphere, which is a protective bubble of magnetic field around the Earth. Now, why we're interested in this, and we and other people, it's kind of an interesting problem because there's a lot of basic physics, but also a very tangible impact on the society. So I pull the White House report called the Report on Space Weather Observing Systems, Current Capabilities and Requirements for the Next Decade. And they list some of the consequences or potential consequences of major events in the Earth's magnetosphere caused by the solar activity. And those include impacts on electric power grid, large-scale blackouts and disruptions, loss of satellite communications, effects on global positioning system, potential permanent loss of satellites and spacecraft. And they give some numbers in terms of the potential cost of some really big events. So one number is that the cost just in terms of the lost satellites could be up to $100 billion, and if nothing is done about the power grid, the potential cost could go up to $1 trillion or more dollars, and repairs would take up to a decade. So obviously, these are the things that drive a lot of research in this area. Now, I don't want to give you an impression that we're solving the whole problem, that we're doing the space weather research in its entirety. What we are doing is trying to understand the fundamental physics issues that are behind the space weather that can potentially feed into some kind of larger scale models that will be used for predictive capability. And one of those processes is called magnetic reconnection. So magnetic reconnection is a process of rapid rearrangement in the topology of magnetic field, which is immersed in plasma, and basically it is a non-trivial process in plasmas because most of the plasmas that we deal with are very good electrical conductors. In fact, they are superconductors to the zeroth order. And it means that evolution of the magnetic field and plasma are coupled to each other. So what you would all sometimes hear is that magnetic field is frozen into the plasma motions. As a result of this, the global evolution, global dynamics of the systems sometimes leads to formation of narrow boundary layers where the magnetic field is highly stressed. And inside those narrow boundary layers, some microscopic physical processes come to play, violate those constraints, and allow magnetic reconnection, which can release this highly stressed, which can release the stresses associated with magnetic field, magnetic reconnection is behind a lot of phenomena in the universe, we think, including these spectacular eruptions on the sun. This is an image, actual satellite image of a prominence rising on the sun. And magnetic reconnection also is a major player in the dynamics of planetary magnetospheres, including that of the Earth. So here's the incoming solar wind from the sun. It brings the magnetic field and interacts with the internal magnetic field of the Earth. And these red rectangles are the primary places where magnetic reconnection can happen in that system. So this cartoon just illustrates what I said in some kind of very simplified form. The blue and red are magnetic field lines. They are pushed together by plasma flows until they can interact and reconnect in some narrow region. The second process that I will be talking about is a plasma turbulence, and of course, turbulence is a big field of study, as you all know. If you recall, there is a classical picture put forward for fluid turbulence, where the energy injected into the system at some large scale is transported down the scales by nonlinear interactions, essentially in a lossless manner, until the scale of those turbulent motions becomes so small that some new processes come in, such as molecular viscosity, and can dissipate the turbulent motions. Now, plasmas are considerably more complicated than fluids. They have magnetic fields, other processes, but those observations, theory, and simulations, they show that something like this probably holds in plasmas as well. So this picture shows a spectrum of magnetic field fluctuations in the solar wind, and you see there's some kind of large inertial range followed by a more complicated region, which is referred to as the dissipation range. And actually, the physics of dissipation range is very complicated. Some subregions of it are not really dissipative. But in any case, one of the central questions, well, there are many important questions that you can ask about plasma turbulence, but one of the questions is, what is that mechanism that dissipates the turbulent motions in hot and rarefied plasmas, such as the solar wind or the upper regions of the solar corona? And this is non-trivial because the Coulomb collisions are not frequent enough in the systems to provide obvious mechanisms for dissipations. So whatever the mechanisms are, they're highly non-trivial. They are collective kinetic processes in the plasma, and that's one of the focus. That is a focus for our research. And on the right, for your amusement, I just put a simulation of flow-driven collisionless turbulence. This is one of our older simulations. And it basically shows you all the complexity that you probably associate with turbulence. This is current density on the grid, so it shows formation of very nice vortices, coherent structures, current sheets, etc. Now, I mentioned that for both magnetic reconnection and the problems in turbulence that we are interested in, microscopic physics is thought to play a very important, actually, key role in the dynamics, and that's what we want to study. So as a result of this, we use kinetic simulations. So simulations solve Boltzmann or Vlasov equations for each plasma species for electrons and ions, coupled to the Maxwell's equations, we use a reasonably well-developed code called VPIC. It was developed at Los Alamos. Typical parameters of the simulations that we ran on Blue Waters are here. So it's several times 10 to the 12 particles, hundreds of terabytes of memory. We run on up to 500,000 cores. All our production simulations are typically smaller, by a factor of a couple. And the another class of models that results from which I'll show are so-called hybrid kinetic simulations. This is where the Boltzmann-Vlasov equation is solved for one of the species, for ions typically, and the electrons are described as a fluid. So these are algorithmically, these simulations are relatively straightforward, and for that reason they have scaled very well on whatever hardware became available recently. So this plot shows progress in particle simulations measured here in terms of the number of particles versus time, and we see here is blue waters, it's up to 10 billion particles, and there is a cheerful extrapolation to the exascale, but we'll see if that's true or not. So now on to some of the more specific things that I wanted to show you. So this is a simulation of decaying collisionless plasma turbulence. What you're looking at is the simulation domain, and the color is the current density. And the significance of the science target of this simulation, the reason why we're doing it is that we want to try to understand the fate of the cascading energy. So as the energy comes down to scale, what are the mechanisms that dissipate it? Where does the energy go? There are several available channels. It can go into ions, it can go into electrons, it can go into thermal part of the population, it could generate energetic particles. And those are the questions that are actually important for the evolutions of the systems. For example, for the global evolution of the solar wind, if there is an energy input from turbulence, we want to know where it goes. And this simulation is unique, as far as we know. It's the first simulation of this type, and in that it's at the same time it's large enough to resolve some of the dynamics in the inertial range, but it also resolves all of the relevant physics, and that allows us to address questions such as the relative importance of various dissipation mechanisms that have been proposed in literature and probably studied with dedicated simulations. But up until recently, it wasn't possible to address the relative importance of the dissipation mechanism, just because you need a simulation that can describe them all simultaneously in a self-consistent manner. And this is what this simulation is. We are specifically interested in information of those current sheets that you see here, those bright lines, and the role that they play in dissipation of energy. I don't want to spend too much time here. I just felt guilty showing you just simple movies, so I pulled out some pictures from a recent paper a few minutes before I started this presentation. But this is the type of analysis that we do on this simulation. So this is basically statistics of the current sheet. We try to current sheets in the domain. We try to identify the dominant fluctuations in the that are present in the system, whether or not they are wave-like perturbations or coherent structures, etc., etc. So the second type of problems that we studied on blue waters is a magnetic reconnection in a global setting like the magnetosphere. And again, the problem, there was a lot of work, and there is a lot of work in this area, but up until recently there were two classes of models. So one is a local model, which could be a tiny dot on this scale, where a magnetic reconnection is studied in a tiny, highly symmetric domain, but with a lot of physics. So essentially all the physics that is important could be included in such a simulation. The second class of models is a global model where, unlike local models, all of the geometry, all of the coupling to the global dynamics is included, but of course you necessarily have to give up something, and that something is the microscopic physics that actually produces the reconnection. So in such models, the connection is typically produced by numerical effects or at best by some prescribed resistivity, which again is not the process that operates probably in the collisionless environment of the Earth. So what we try to do in this work is to perform simulations that address this middle ground, somewhere in between this and this. We have a two-dimensional geometry which is reduced compared to the real 3D structure, but we still retain all the physics. And this class of models we think are very important because they provide a lot of information on how reconnection couples to the global dynamics. And here are some of the findings from these simulations. Well, some illustration of some of the processes that we looked at. Some multiple X-line on the thin boundary that separates the solar wind and the magnetosphere. We study how these reconnection sites interact with each other. What are the observational signatures that could be used to search for these processes in say, satellite data. Let me skip this. And the final class of simulations that I want to talk about are the hybrid simulations. So in hybrid simulations, we, as I mentioned before, we give up electrokinetic physics, but retain ion kinetic physics. And that allows us to conduct simulations that are much larger in physical scales, but still retain a lot of interesting physics. And our focus here was on the interaction between what's known as the force shock turbulence with the bow shock. Bow shock is this is the shock that stands in front of the Earth's magnetosphere. And what you see here, this is a 2D simulations that we ran before starting the work on blue waters. It's a global simulation. There is a dipolar magnetic field somewhere here, which represents the magnetic field of the Earth. Solar wind comes from this domain, brings with it some magnetic field, which in this case has a nearly radial orientation, so it's oriented like this. And it was known before that in a situation like this, the ions can get reflected from the shock, travel backward upstream, and drive turbulence in this force shock region, in the region before the shock. What we discovered in those 2D simulations, however, is that the interactions of this force shock turbulence with the shock itself leads to just an incredible variety of interesting features in the shock and in the magnetoschist, this region of shocked plasma behind the shock. And what we are now using Blue Waters for is to do the 3D version of this simulation. So these are very, very interesting, very exciting simulations, but they are restricted in their geometry because the flow has only two ways to go, essentially up and down. In 3D, the flow structure can be quite a bit more complicated, so it's very important to actually do a three-dimensional simulation. And those simulations are actually still running on Blue Waters, so I'm just showing you a few snapshots from the current state of affairs. And what we see here is that a lot of these processes that we identified in 2D are still present, and we are really excited to see how they will work in this three-dimensional case. So here is a plot, for example, of this is a temperature parallel measure of the width of the distribution parallel to the magnetic field. So this region just tells you that there are reflected ions and they are going to drive turbulence here. There are a lot of other interesting features in this kinetic simulation. That have not been seen before. For example, this is a turbulent X point. All right. Well, I'm going to leave you with the summary and hopefully take a question or two.